All right, so we're starting chapter 8. This is section 8.1. We're going to be testing the difference between means. So the big difference between chapter 7 hypothesis testing and chapter 8 hypothesis testing. Chapter 7, we just had one sample and we went with that one sample from a particular population and tried to do some inferential statistics. Chapter 8, instead of just looking at one sample from one population, we're going to be taking a sample from one population and comparing it with a sample from another population. Okay? So when we do that, when we're comparing samples, one thing we got to think about are independent versus dependent samples. So those words are coming back for us. So 8.1, we're going to be dealing with independent samples where sigma 1, because there's one population and then the other population's standard deviation is known. Okay? All right. Independent. What does independent sample look like? So say I have a sample 1. So I've got some dots over here. And I've got a sample 2. Got some dots, some random dots over here. Those are my data points. So what does it mean to be independent sample? The sample selected from one population is not related to the sample selected from the second population. Okay? So what do I mean by this? Right? So here's an example. Say we have a sample, so some sample where we're talking about systolic blood pressure. So the blood pressure of 30 females is sampled. Okay? And then we do a second sample and we take the systolic blood pressure of 30 males. Okay? Now, why are these independent samples here? They're independent because they're different people. That are sampled. Okay? So if you're in group 1, guess what? You're part of the females. You're not going to be in group 2, which those participants were all the males. Okay? So those are independent of each other. All right? One female of one person's blood pressure is not going to affect the blood pressure of some other person. All right? Unless they're living together and married, right? Okay. So we're assuming they're independent. So those are example of 2 independent samples. Let's take the other side of the coin. Dependent. Dependent samples. All right, so maybe I've got 1, 2, 3, 4 and 1, 2, 3, 4 over here. So maybe this is sample 1 and sample 2. Okay. So dependent. So maybe this maps right over here. This little dot, that sample pairs up with this one. This one matches over here, and then this last one goes straight to this one here. Typically dependent, all right, is before and after results. Ooh, results. Okay? typically it's for the same person or object. Okay? So like, just to give you a formal definition like we did for independent, each member of one sample corresponds. What does it mean to correspond? I get map from here exactly over to there. Corresponds to a member of the other sample. Okay? This is known as paired. Important word there for you. Might see that in the future. Or matched data sample. Okay. So your example here, before and after data, maybe it's a person's weight before they go on a diet. Okay? Maybe this diet is promising, if you do our special diet, in 3 days you'll lose 45 pounds, right? That's probably not safe. Okay? So be careful. Sample 2 is the person's weight after maybe 6 weeks. Okay? So it's the same person, right? It's got to be the same person, okay? How goofy would it be, if say, I'm going to go on a diet, okay? And I say to my wife, all right, we're going to measure your weight, okay? We got your weight recorded, all right? And yeah, I'm not going to tell my wife's weight on camera because I like my wife and I don't want her to kill me, right? So her weight is X, right? Okay, so Sarah's weight is X, okay? And then at the end of 6 weeks, I get on the scale and I weigh a lot, okay? Where my wife does not weigh much at all. Now, what's going to have happened there? It will look like I gained a whole lot of weight, but that's kind of dumb, right? Because why would I measure her weight and then compare it with my weight, right? So when we're talking about before and after data, we're talking about before and after data on the same individual. So I want to compare, what was my weight before I started the diet. So before the diet, I weighed, a lot, right? But after the diet, I weighed a lot minus 5 pounds, okay? So I'm comparing before and after data with, if this is A here, this is A over here, right? If this is B here, this is B over here. If this is C here, this is C over here. And if that's D there, that's D over there. It's the before and the after that's going on here, all right? So that's why we call it paired data, okay? The data is dependent because the same people were selected. All right. 2 sample hypothesis test. With independent samples. So we are testing a claim concerning the difference between the parameters in two populations. There's two populations here. Not the values of the parameters themselves. Okay? So the way we set this test up, we have a null hypothesis. Look familiar? The null hypothesis, the HO, okay, is a statistical hypothesis that usually states there is no difference between the two populations, right? No difference. Now, with the null hypothesis, it's the same thing. I have equality. All right, I have equality here. The alternative hypothesis, the HA, is a statistical hypothesis that is true when H naught is false. This is the opposite. What is the opposite of less than or equal to? Greater than. What is the opposite of equal to? Not equal to. What's the opposite of greater than or equal to? Less than. All right? There's no equal sign in the HA. Only the HO has the equals. We assume no difference. So how do we set up our test? Okay, how do we set up our test? So the HO can be set up in three different ways. The HO and the HA. The HO can be equal to, we have the two population means are equal to each other. The opposite of that is mu1 not equal to mu2. Okay? The next way, the HO can be mu1 is less than or equal to mu2. Therefore, the HA is going to be mu1 greater than mu2. And the last way is the HO, where the population from the first mean is greater than or equal to the population from the second mean. And the HA is mu1 less than mu2. Okay? So, what does this mean? What does this mean here? Well, if I take mu1 equal to mu2, what can I do? I can solve to get to be 0. If I subtract mu2 from both sides, so I get mu1 minus mu2 equals 0. Okay? Over here, if I do minus mu2 again, I get mu1 minus mu2 less than or equal to 0. And then over here, if I take this and subtract mu2 from both sides again, I get mu1 minus mu2 is greater than or equal to 0. Okay? We always assume there is no difference between population means and then if we run the test and find evidence to the contrary of that assumption, meaning yeah, there's obviously a difference because the probability that there's no difference is like 0.001, right? It's really small. Then we conclude, therefore we reject the HO and we say what? We say that the alternative has to be true. There actually is a difference, okay? So we start with the HO in assuming that there's no difference, right? So we're just saying that there potentially might be a difference, all right? They're not trying to say, okay, they're not trying to, so there's something, little known fact in America, there's income wage inequality between male and female. A lot of times, which is wrong, is that the female does the same exact job as the male, and they are paid maybe 70 cents on the dollar for that same work, okay? So a statistician, an outside statistician, might be hired to come into a company and run the numbers on the payroll and say, okay, is there any bias going on here? Well, what would they do? They would run in and they would do this two-sample hypothesis testing, and they would look at the average pay for females who do this particular job and then the average pay for all the males that do this particular job. And you run the test assuming that there's no difference between the two. But if the test comes back with such a low probability of that being the truth, then we have to reject the assumption that they are equal and say they're different, right? But I'm not saying that one is bigger than the other. What I'm saying is that they are different, all right? And so by some measurable amount, we're not asking, is their difference more than $1,000? If we were asking something like that, then your problem would not be, mu1 minus mu2 less than or equal to 0, or mu1 minus mu2 greater than or equal to 0. It would be like mu1 minus mu2 greater than or equal to $1,000, okay? So that would be the test, all right? But since it's 0, all we're doing is we're testing to see, is there a difference, yes or no, okay? This type of problem would be the next level in statistics, all right? So we're not going to do that type of problem in this class. It's really not that much harder. You're just basically adding in a number here, okay? But we're not going to get into that. So let's talk about how to run the test. It's a two-sample z-test. This can be used to test the difference between two population means, mu1 and mu2. When there are 4 criteria to use this, sigma 1 and sigma 2 are known. Okay, sigma 1 and sigma 2 are known. Number 2, it's a random sample. Number 3, samples are independent. Number 4, the population is normally distributed, or both in 1 greater than or equal to 30 and in 2 greater than or equal to 30. So the populations either need to both be normally distributed, or we need to both know that they both exceed the 30 limit, or you could have some combination, like one could be normally distributed and the other one be greater than or equal to 30. But looking at each population for mu1 and mu2, each one needs to either satisfy normally distributed or in greater than or equal to 30 for each of them, okay? And if the above is true, so if those 4 things are true, then we can run the test. The sampling distribution for x bar 1 minus x bar 2, this is the test statistic. So if you're asked to calculate the test statistic, this is the test statistic for the 2-sample z-test, okay, is normally distributed with a mean of mu sub x bar 1 minus x bar 2 and standard error of sigma sub x bar 1 minus x bar 2. Okay, so how do I calculate this right here? This is equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so that is my standard error. All right. Now, how do I get the standardized test statistic? The standardized test statistic, what is it? It's Z equals the observed difference minus the hypothesized difference over the standard error. So what does Z equal to? It's the observed, which is the samples, subtract their means, subtract the sample means, minus the hypothesized difference, mu1 minus mu2. Look, if we knew mu1 and mu2, we wouldn't need to run statistics, okay? The whole point of doing statistics is to estimate mu1 and mu2 with x bar 1 and x bar 2. That's the power. All right, divided by the variance of the first population divided by how many are in the first sample, plus the variance of the second population divided by how many are in the second sample. Okay? Now, what do we know? In the HO, with the null hypothesis, what do? We assume there's no difference. If there's no difference, what does that mean? If I subtract mu1, all right, so if mu1 equals mu2, that means there's no difference in the means, right? So what is mu1 minus mu2? So if I subtract mu2 from both sides, what do I get? Mu1 minus mu2, that's equal to 0. So in the HO, in the null hypothesis, this thing is limiting to 0. Okay? So really, it kind of makes your life a little bit easier because the formula then becomes x bar 1 minus x bar 2 over square root sigma 1 squared over n1 plus sigma 2 squared over n2. Okay? All right, so that's it right there. Okay. So now what I want to do is I want to start a new video to work through these problems. Okay, guys.